Okay, but what exactly is a Gaussian or a normal distribution? I showed you a graph. The first thing that's different is the Gaussian distribution is for real variables, as I said, and both binomial and Polsson distributions apply to discrete variables. As we shall see, even for discrete variables, if many trials are present and the change between the values is small, continuous distributions are assumed because the math is easier. By noting that the Polsson distribution becomes essentially symmetric about its mean for means greater than or equal to 20, we can use the normal distribution, g sub x, given by the hideous formula you see here, where m is the mean of the distribution and sigma is the standard deviation of the distribution. Note that the mean and the standard distribution can be arbitrarily set for Gaussians rather than being the intrinsic property of the distributions as it is for the Polsson. We cheat and set the standard deviation of the Gaussian to the square root of the mean as if it were a Polsson, and then we use all the mathematical apparatus for the Gaussian. As you saw, it works well. The conclusions we drew above apply only to a measurement of the number of successes. In radioactive decay or nuclear counting, we may directly apply that the standard deviation is the square root of the mean only if the x represents a counted number of successes. That is, a number of events over a given observation time recorded from the detector. We cannot use this relationship with count rates, sums or differences of counts, averages of independent counts, or any derived quantity. Because students miss this concept so often, bear with me and I'll repeat this. The only flippin' thing that is Polsson or Gaussian or even binomially distributed are the counts themselves. That's it. As soon as you add them, subtract them, multiply them together, multiply by a constant, divide them, or even look at them hard, all bets are off. Well, what are we going to do? Fear not, help is on the way. For all quantities other than the directly detected number of counts, we can determine the uncertainty by propagating the errors of any of these operations made by adding two counts, dividing by a constant, subtracting off a background count rate, multiplication or division of counts, producing a mean value of multiple independent counts, combining independent measures with unequal errors. To do these mathematical feats, we need to use, ta-da, the error propagation formula shown here. For those of you who actually know what the backward 6 means, you can easily derive what I'm going to show you next. When you're adding or subtracting two measurements, each with a given uncertainty, the uncertainty of the final quantity will be produced by summing of the errors of the individual parts squared. Or if x and y is summed or subtracted to produce u, then the standard deviation in u is the square root of the sum of the standard deviations of x and y each squared. As a side note, now you can see why statisticians love variance. Said their way, the variance of u, the sum, is equal to the sum of the variance of x and the variance of y. Well, what if we multiply a count by a constant? If we divide or multiply a quantity with a known uncertainty by a constant, that is a number with no uncertainty, then the standard deviation of the product is simply equal to the standard deviation of the original quantity multiplied or divided by the constant. Thus, if u equals ax, where a is a constant, then the standard deviation of u is equal to a times the standard deviation of x. If we multiply two quantities together, the fractional standard deviation of the product is determined by summing the fractional standard deviations of the original quantities squared. Or, if u equals x times y, then the standard deviation of the product is sigma u divided by u quantity squared equals sigma x divided by x quantity squared plus sigma y divided by y quantity squared.